A hyperscale artificial intelligence data center drawing over 10 megawatts operates as a continuous, massive baseload energy drain. Plugging these extreme industrial loads into the open public electricity grid is an obsolete engineering practice. Forcing data centers onto standard municipal grids triggers systemic voltage vulnerabilities and pushes hundreds of millions of dollars in extreme infrastructure debt onto ordinary citizens. All future hyperscale AI loads must be legally mandated to co-locate directly at primary power generation nodes. In strict industry nomenclature, this required architecture is defined as a behind-the-meter, or BTM, physical integration. The facility sits entirely on the generator's property, completely bypassing the utility's transmission meter. Evaluating the viability of this mandate requires a forensic, comparative analysis of both deployment models. We evaluate the data across three specific vectors: regulatory physics, ratepayer insulation, and thermodynamic synergy. Measuring the physical and economic outputs across these three pillars identifies the legacy open grid model as a physical engineering failure that must be strictly prohibited by regulators. Standard open grid facility deployments are currently paralyzed by a 5.2-year PJM interconnection queue delay. When a massive new load attempts to inject onto the public grid, regional operators must run complex, multi-year transient stability models across multiple states to prevent widespread grid collapse. Attempting to bypass these safety reviews through expedited interconnection tracks introduces severe systemic risk. Compressing a multi-year dynamic contingency study into 10 months forces engineers to rely on generalized models, creating localized voltage collapse vulnerabilities, where a sudden massive spike in data center demand could trigger cascading blackouts. A behind-the-meter physical integration bypasses this hazard. The data center hooks directly into the generator's side of the substation, consuming the power locally on private property before it ever reaches the interstate transmission grid. This model illustrates generation netting. If a 1,000 megawatt power plant routes 200 megawatts directly to an adjacent server facility, it drops its transmission output to 800 megawatts. By injecting less power into the public grid, the generator officially reduces its capacity interconnection rights. Because the power plant is placing less stress on the regional grid, PJM does not need to run multi-year transmission stability or grid expansion studies. The 10-month timeline for behind-the-meter safety configurations verifies local emergency backup switches. This contrasts with the fast-tracking of open grid connections that obscure regional blackout risks. Generation netting resolves the queue delay by physically decoupling the data center from the regional transmission network. This conversion turns a sprawling grid injection problem into an isolated, local netting solution. Integrating extreme industrial loads introduces the financial threat of stranded assets. If the artificial intelligence market cools, or a tech operator abruptly vacates a massive facility, the local utility is left holding hundreds of millions of dollars in unamortized debt for specialized substations and high-voltage lines. This tracks utility cross-subsidization. When a corporation abandons an open grid facility, the utility petitions to reclassify the infrastructure as a public asset. The unamortized debt then rolls into the general rate base, forcing homeowners to pay off the abandoned facility through permanent fee hikes. State legislatures are implementing a strict statutory correction: mandatory large load tariffs for any facility drawing over 10 megawatts. The first firewall mechanism enforces binding, long-term operational commitments, mandating a strict 15-year minimum contract tenure between the developer and the utility. Second, these tariffs enforce an 85% take-or-pay minimum. Data centers are legally billed for 85% of their contracted peak demand capacity, guaranteeing utility revenue. Third, developers must post massive upfront financial security. Before a single line is engineered, the operator must deposit capacity collateral equivalent to $1.5 million per megawatt. Consider an early abandonment scenario under this new tariff structure, where a facility breaks its contract in year 3. This illustrates the unamortized capital clawback. The departing operator is legally liable for an immediate cash payoff equaling the net book value of the dedicated grid infrastructure. To clear this debt, the utility instantly liquidates the upfront collateral, entirely bypassing the state regulatory board. These statutory penalties establish an absolute economic firewall. The dedicated asset is paid for in full by the entity that requested it, ensuring that zero industrial risk is passed through to the public rate base. A 10-megawatt hyperscale data center is a continuous, massive industrial heater, converting nearly 100% of its electrical input into thermal energy. Standard data centers sitting in isolated office parks rely on massive cooling towers, evaporating millions of gallons of treated water solely to vent that industrial heat into the sky as waste. Co-locating the facility directly at a generation node creates the physical advantage of zero-distance thermal transport, eliminating the degradation that ruins municipal district heating pipes over long distances. Nuclear and natural gas power plants operate on the Rankine cycle, a thermodynamic loop where water is pressurized and boiled into high-pressure steam to spin electricity-generating turbines. This schematic shows an internal efficiency drain. To prevent thermal shock, the plant extracts high-grade steam from the turbines to preheat incoming feed water. Every pound of steam siphoned off fails to turn the generator blades, directly reducing the plant's net electrical output. A co-located data center utilizing a direct-to-chip liquid cooling loop captures server waste heat at a stable 100 to 110 degrees Fahrenheit. This heated liquid is piped into a liquid-to-liquid heat exchanger at the power plant's cold water intake. The data center's thermal waste transfers into the incoming feed water, pre-warming it. The power plant automatically detects this temperature increase and drastically reduces internal steam extraction. The saved high-pressure steam remains inside the turbine housing, driving the generator blades longer and resulting in a surge of turbine work. This optimized loop enables the power plant to output more net megawatts of electricity into the grid using zero extra fuel consumption. By capturing and reusing low-grade thermal exhaust, behind-the-meter co-location transforms a standalone data center into a highly efficient thermal partner. Evaluating these three pillars identifies the legacy open grid model as a physical engineering failure that aggregates thermodynamic waste and economic risk. Generation netting permanently eliminates PJM interconnection queue delays and localized transient stability blind spots. Strict capacity collateral and long-term take-or-pay mandates insulate residential utility ratepayers from industrial market volatility. Direct liquid loop thermal exchange leverages data center waste heat to boost power plant efficiency without adding extra fuel or carbon. To stabilize the grid transition, regulators must implement a line-in-the-sand grandfathering protocol. All existing standalone data centers are classified as a static grandfathered reality, ensuring immediate economic stability for current utility operations. Mandatory co-location ensures tech corporations bear the full cost in their specialized industrial loads, shielding public infrastructure from private capital risk. For all future development permits exceeding 10 megawatts, high-fidelity behind-the-meter co-location must be the absolute mandatory standard.